Our paper is called Extracting Dual Solutions via Primal Optimizers, and my co-authors are Yair, Arun, and Aaron. So as a roadmap of this talk, we're going to motivate a fundamental problem in mini-max optimization and state our general result. And we'll then go over three applications of our general result, and finally we'll conclude. So the general setting we're going to look at is we're going to have an objective psi, which is a function from, it takes a variable in Rd and a variable in Rn and returns a real number. And it is convex in the first d variables and concave in the last n variables. And we're going to have convex constraint sets x and y. And with this setup, we're going to look at associate two optimization problems. So the primal optimization problem P we're going to minimize over the x variables a function f, which is defined pointwise by maximizing psi over the y variables. And the dual optimization problem D is defined analogously, where we're going to maximize over the y variables a function phi, which is defined pointwise by minimizing psi over the x variables. And we're also going to assume that this setup satisfies what's known as the minimax principle or strong duality, which says that if you take any optimal point for P and optimal point for D, their values are the same. And we give general assumptions under which this holds in the paper, but for example, this holds if the constraint sets are bounded. Okay, so one canonical example is bilinear matrix games where you're going to have this objective of x transpose ay plus b transpose x plus c transpose y, and the constraint sets x and y are either the unit Euclidean ball or the probability simplex. And this has many applications, including zero-sum games, linear programming, hard margin support vector machines, and minimum enclosing and maximum inscribed ball. Another example is where psi is given by this weighted average of a set of n functions fi evaluated at x. So here, the dual constraint set is a subset of the simplex. And in particular, this encompasses a variety of distributionally robust optimization problems. And finally, as an example of a different flavor, if you have some convex function h, you can form a natural minimax objective associated with that convex function h. It's called what's known as the Finchel game, and it's given by x transpose y minus the convex conjugate of h. And in particular, this particular minimax objective has been used in the past to recover optimal algorithms for convex minimization via a minimax framework. So it basically allows you to lift some kind of convex minimization problem to a minimax optimization problem, and then you can apply the many powerful tools for minimax optimization. So as motivation of the general problem we consider in this paper, um, there's before this paper, there were applications where the cost of computing, and as far as we knew, the cost of computing an epsilon optimal solution to the primal optimization problem P was strictly cheaper than the cost of computing an epsilon optimal solution to the dual optimization problem D. So the fundamental question we ask in this paper, and two recent examples are in bilinear matrix schemes and distributionally robust optimization. And the fundamental question we ask in this paper is whether this is actually the reality or whether it's possible to design some kind of general framework which solves the dual optimization problem at the same cost as the primal optimization problem. And in particular, we can formalize this. We can ask, can we solve the dual optimization problem given access to a black box oracle which solves the primal optimization problem? In other words, the only way we can access psi and the constraint sets x and y is through this black box oracle which solves the primal optimization problem. But this isn't quite enough because intuitively we need to somehow have some access to the space of y variables. So we ask the same question, but additionally given access to a black box oracle for computing a dual best response. So given any primal point x, the dual best response is the maximum over y of psi xy. And in particular, in most applications, and it's going to be the case that not every application, but most applications, it's often the case that uh, the cost of the first oracle is strictly more expensive than the second oracle, um, and thus you can in some cases you can think of the second oracle as kind of being for free, but not every application. Okay, so altogether, we ask the question, given only a black box oracle, which solves the primal problem to epsilon accuracy, and a black box oracle for computing an exact dual best response to any primal point x, can we obtain an epsilon optimal solution to the dual optimization problem D? And we give a general affirmative answer to this question, which is basically the answer is yes, as long as you can additionally access regularized versions of these two oracles. So towards stating our formal result, we're going to define what it means to have a regularizer on the dual constraint set Y. And we're going to, you can choose any norm you want on Rn. And then we're going to define a distance generating function, which is one strongly convex with respect to that norm. It's a distance generating function over the dual constraint set Y. And in particular, if you're not familiar with this, you can just think of either of these examples. So if you're working with the L2 norm, the standard distance generating function is the Euclidean norm squared. And if the dual constraint set is a subset of the simplex and you're working with the L1 norm, then the standard distance generating function is negative entropy. And uh, for the distance generating function we've chosen, we're going to define a Bregman divergence, which is just a notion of distance between points in the dual constraint set. So in particular, you can just think of these two examples where for the first example, the Bregman divergence is just the Euclidean norm squared of the difference between the vectors. And in the setting where Y is a subset of the simplex and you're working with negative entropy, the corresponding Bregman divergence is just given by the KL divergence. So having defined a notion of regularization over the dual constraint set, we can now formally state the definitions of the regularized versions of the two oracles mentioned previously that we consider. So to do so, we're first going to define a regularized version of the function f, which appears in the definition of the primal optimization problem. So we're defining this regularized version of f, and this regularized version of f is defined for a given center of regularization q and a parameter lambda greater than 0, which corresponds to how much regularization you're adding. And it's defined exactly like f is defined, except instead of just maximizing, instead of feeding in a point x and returning the maximum of psi maximized over the y variables, you're going to first subtract this regularization term in the y variables, which is a Bregman divergence from q to y. So having defined this regularized version of f, we can formally state the definition of what we call the dual regularized primal optimization oracle, or DRPO oracle. And instead of returning an in this case epsilon sub p optimal solution for the primal optimization problem P, the DRP oracle instead returns an epsilon sub p optimal solution for minimizing the regularized version of f over the primal constraint set x. And then likewise, we can define the natural corresponding regularized version of the best response oracle. So in this case, we call it the dual regularized best response oracle, or the DRBR oracle. And so again, given your regularization center, your level of regularization, and a primal point x, instead of just returning the maximizer over the y variables with respect to psi, it's going to return the maximum over the y variables of psi minus the exact same regularization term, which appears in the regularized version of f. And in particular, in every application we consider, and the vast majority of applications, these regularization is only going to help you. So these oracles are only going to be cheaper to implement than their non-regularized versions. So you can kind of think of regularization as being without loss of generality in that way, or only something that can help you in most applications. Okay, so now we're going to state our general theorem. So um, given some initial point in the dual constraint set y0 and constants L and B such that the dual function phi is L Lipschitz with respect to the norm we've chosen over the dual constraint set y. And also you have this Bregman divergence bound between y0 and some optimal point for the dual optimization problem D. So in particular, we can choose the norm we work with and the distance jittering function we work with and the corresponding Bregman divergence. So we can choose those to make L and B as small as possible. Then for any target precision epsilon greater than 0, and this value of k, which is logarithmic in all of the problem parameters, there exists an algorithm which makes at most a logarithmic number of calls to both of the oracles. And the dual regularized primal optimization oracle is always called to a precision of epsilon over a logarithmic factor. And this algorithm returns exactly what we want, a point y, which is epsilon optimal for the dual optimization problem D. So in particular, note that this L and B, these are really weak assumptions because the guarantee is logarithmic in these parameters. And also note that if this sort of if the cost of the dual regularized primal optimization oracle to precision epsilon divided by a logarithmic factor, as well as the dual regularized best response oracle, are both dominated by the cost of solving the original primal problem to precision epsilon up to multiplicative logarithmic factors, then this theorem immediately says that you can indeed solve the dual optimization problem at the same cost as the primal optimization problem up to multiplicative logarithmic factors. This is typically going to be the case where the cost of everything is inverse polynomial in epsilon, in which case the additional cost is going to be from solving to a precision of epsilon over a logarithmic factor and running for a logarithmic number of rounds. And so you're basically going to get the same cost as solving P, but with these additional multiplicative logarithmic factors from applying the theorem. And we note that, so this is really actually a corollary of a more general result in our paper. In particular, it comes from fixing a particular choice of parameters in that more general result. And we actually give alternate parameter schemes, which in certain applications can avoid this multiplicative logarithmic cost over the cost of obtaining an epsilon optimal point for the primal optimization problem P, which you're typically going to incur if you just apply this theorem on this slide. And in particular, in our third application to computing stationary points, that becomes really critical. We use that alternate scheme to avoid additional multiplicative logarithmic factors to get an optimal complexity. So we've motivated our problem and we've stated our general result. And now we're going to present three applications of our general result. So the first application is to bilinear matrix games where psi is given by X transpose AY for a matrix A in D by N. And we're going to consider two settings for the constraint sets. So in the ball setup, the primal constraint set is going to be the unit Euclidean ball. And the dual constraint set is going to be the probability simplex. And we're going to make a standard appropriate normalizing assumption on the matrix A. And in the simplex setup, both of the constraint sets are the probability simplex, and we again make the standard natural normalizing assumption on the matrix A. Then this is these are the primal and dual optimization problems for this particular application. And recently, Carmen et al. Gave a runtime for obtaining an epsilon approximate minimizer of the primal optimization problem in the setting. But their algorithm only gives an epsilon optimal solution for the primal, and they leave it as an open question whether it's possible to obtain an epsilon optimal solution for the dual with this same runtime. And so we apply our theorem and we answer this open question and we obtain an algorithm with the same runtime for obtaining an epsilon approximate maximizer for the dual optimization problem. And we also observe that specifically in the simplex setting where the constraint sets are symmetric, we obtain a new state-of-the-art runtime for solving the primal as well. Our second application is to a particular distributionally robust optimization problem, conditional value at risk, DRO, which is a canonical and very fundamental distributionally robust optimization problem. And here, so you're going to have in functions, fi, which are convex bounded in one Lipschitz, and the dual constraint, so the primal constraint set in this application is going to be some convex compact set, and the dual constraint set is given by the probability simplex, except you're going to add this additional constraint on the L infinity norm of the probability distribution. So you're going to have some parameter alpha between 1 over n and 1, which you're going to set in advance, and you're going to enforce that the L infinity norm is at most 1 over alpha n, and this is known as the uncertainty set. And this is the primal and dual for this application. And in particular, the primal here, for example, if you have n data points in your training data set and you're trying to learn a model represented by parameters x, then the primal optimization problem corresponds to training some sort of classifier which performs well on your training set. And in particular, it recovers empirical risk minimization. In other words, so fi here is the loss of the model on the ith data point, in which case, if alpha equals 1, you're just minimizing the average loss, so it's empirical risk minimization. And the other extreme case of alpha equals 1 over n corresponds to minimizing the maximum loss. So CVAR is interpolating between these extremes. The complexity model we'll look at is the number of first order queries, meaning you're going to get fi of x and grad f of I of x to obtain an epsilon suboptimal point. Recently, Levy et al. Achieved a complexity of alpha to the -1 epsilon to the -2 for solving the primal optimization problem. And we apply our general result to obtain a new state-of-the-art complexity for obtaining an epsilon optimal solution for the dual optimization problem in this application. And in particular, this additional additive in factor is due to the dual best response oracle. And the previous best for solving the dual was in epsilon to the -2. So ours is only better since alpha is between 1 over n and 1. And then for our final application, we're going to look at the problem of computing an approximate stationary point of a convex and beta smooth meeting the gradient as Lipschitz function h. So given some gamma greater than 0, we're going to ask how many gradient queries are needed to obtain a point x such that the Euclidean norm of the gradient of h is bounded by gamma. And if we let delta denote the initial suboptimality, it's been shown that a query complexity of the square root beta delta over gamma is optimal. And in particular, this upper bound has only been achieved pretty recently And it's been a significant recent interest. There's been several follow-up works. So as as an example of the broader applicability of our framework, we apply our framework to recover this optimal gradient query complexity for obtaining a approximate stationary point. Okay, so recall the setup and recall the setup for applying our framework. And this is just the definition of the convex conjugate of a convex function. And we're going to choose psi to be the Finchel game. So the inner product of x and y minus the convex conjugate of h. And we're going to set the dual constraint set y to be Rn. Then if we work out what the function f, which appears in the primal optimization problem P is in this case, it's given by the conjugate of the conjugate of h, which is just h of x. So in other words, the primal optimization problem is exactly minimizing h of x over the primal constraint set x. Also, you can just show using standard properties of the convex conjugate that a dual best response, again, a dual best response is taking some primal point x and returning a point y, which maximizes psi in the y variables in response, can be computed using a gradient computation. So if you want the dual best response to some primal point x, you can just take the gradient of h at that point. And we show that these properties extend naturally to appropriately regularized versions of psi. In particular, the dual regularized primal optimization oracle corresponds to just approximately minimizing a rescaled and recentered version of h. So in particular, we can implement this oracle by using some fast method for minimizing a convex and smooth function using gradient queries. And the dual regularized best response oracle, again, can just be computed using a single gradient query to h at some translation and scaling of the primal point given as input x. And to get a sense of what the analysis looks like here, what we prove is that with this setup, we show that if some point y is approximately optimal for the dual objective D, then you can obtain a bound on the Euclidean norm of the point y. And then the way the proof of correctness works is through our general framework, we obtain an approximately optimal dual point as a best response to some primal point x, which we also have. And then because this dual point is approximately optimal, we can just apply the line above to obtain a bound on the norm of this dual point. And because we know that the best response oracle is just some gradient computation, we can immediately conclude that the gradient of h at x is small, which immediately implies that x is an approximate stationary point. So in conclusion, we give a general framework which reduces maximum optimization to minimax optimization. The design and analysis of the framework relies on recursive regularization, and we refer to the paper for details. We apply our framework to obtain new state-of-the-art guarantees for bilinear matrix games and conditional value at risk distribution robust optimization. And as an illustration of its broader applicability, we also recover the optimal complexity for computing an approximate stationary point of a convex function.